Hi.
Hello. Can you hear me?
Yeah, hi. Hi. I can hear you.
Sudeep. Yeah, right.
Yes.
Yeah.
Surit,
Hi.
Surit.
Ah, okay. So the links that you have shared, no, on the uh, Google Doc, please share it once again in the chat also once our people join, so that if somebody has not yet downloaded it, they can do it right away.
Okay.
Yeah.
Yeah.
And thank you so much for doing this for us.
Yeah, no
I hope
problem.
you. Yeah. Yesh is not joining.
No, I think he's joined right now.
Oh,
He won't be joining 5 to 6, but he'll just, I think, come to say hi.
okay. So we'll let's wait. We have some 22 members. They'll join
Right.
in few minutes.
Yeah.
I'll introduce to them as well. One of our members is already here. Iman. Hi, Iman.
Hello.
I think she's on mute. Iman, can you hear us?
I think she dropped a chat.
Okay, okay.
Yeah. So, of course, this will be recorded, right? The
Yes,
meeting
yes.
will be recorded.
Let's record it from the stop the recording and start it when you're beginning the session, no? So that way we won't need to edit it before putting on our channels and website.
Actually, I don't know how to do that.
No, the recording is in progress, no? So you can stop the recording and restart it when you begin the session. Or is it already it is already being recorded, all this?
It is, yeah,
Don't
it's
worry.
already started. So we'll edit that afterwards. It's just a 2-minute job,
Okay.
1 minute job. It's fine.
Okay. Yash is here as well. Hi, Yash. I have. Are you guys getting some disturbance from my background? I'll mute.
No, it's okay. It's quite all right.
Okay, okay. So for the last two workshop, the Indian people can pay easily via UPI, but the amount is too small to transact internationally. So what I'll do is, if it's possible, then I'll make a gift card and send it to you or something. Like my PayPal account is suspended because last time we collected membership fees via PayPal, and what happened was that it was dormant for all these years, and suddenly there were so many transactions, and then they suspended it. So
Okay.
yeah, even that's not a good idea. But Razorpay, you are allowed to take international payments if you have registered or something. So let me know how you'd like to our members to pay, and I can see that our members have joined.
Yeah.
So
We can start in, I think, 2 more minutes.
yeah. Correct. Mm. One of our members is saying that, can you please send the link again? It's not working. I'll say join using meeting ID. And that, let me find that uh, Open API and Web Power. So it is supposed to be downloaded. It's a software, right? And Web Power as well. Requesting everyone to kindly download both the softwares that have been recommended by our host, Epi Power, and the other one is check. I'll also share the link on the group itself, so you can, if you haven't already downloaded, please download it right now. Open API and Web Power. So Web Power is an online tool, right? It is not a software. I can't hear you. Either you are muted or I am.
Oh, sorry. Yeah, both are online tools. OpenAPI and WebPower both are online tools.
Okay, both are online. That is great.
So everybody, I have shared both of these links on in the chat. So I think all of you can go ahead and just keep them open in your web browsers. So
Yes.
let me start now. I think it is 5:02. So let me start by first introducing myself. I'm Surat Panchavag, and I am a consultant statistician at Sancheti Hospital in Pune. I'm also an intern, a medical intern. Just finishing my medical school. I have an interest in biostatistics and research, and that is how I'm associated with Requir Statistics. So this, this will be a series of interactive tutorials. These won't be didactic lectures, although you might find today's lecture to be a little didactic, or me speaking and you absorbing most of the things, except for sample size calculation. Because the reason is because I want everybody to have a solid base about what we are going to do in the next few sessions. So the next few sessions will be entirely practical sessions focused on how to use the JASP software to perform, to understand firstly, and then perform biostatistical analyses on data. And since they will be practical sessions, I hope everybody will find it interesting and enjoyable, and not get bored by it. hopefully. This session, although to reiterate, will be a little theoretical, but I hope so. I hope everybody is ready with both of these sites, have opened both of these sites. And I request everybody to be ready to click screenshots of the slides for easy viewing. So, because some slides have information packed in them, it won't be too heavy, but you may want to refer to that information later on, right? So I think we can start. Let me start by sharing.
So
Yeah,
slides you can share with me on the email. I'll forward it to them so that they can have it in one place only. If that's comfortable with you, otherwise it's
yeah,
all right.
yeah. No, I'll share the slides with you, but you can take screenshots of the slides where I as well,
Okay, sure.
both of
Sure.
right. So so I hope everybody can see the entire screen now.
Yeah, we can see.
Okay, great. So uh, I'll be sharing these resources as well afterwards, but you can click a screenshot of this slide right now. These are resources which are extremely useful, which all of you guys can use, and from which I have prepared this lecture. So just take a screenshot of this and I will move on. So when we talk about research, the first thing which we want to talk about is the methodology of a research. Because when you think of a topic, a research topic, the first thing you would want to focus on is how are we going. So first of all, obviously, when you're thinking about a topic, you will think about the aims, primary objectives of the topic, and why you want to do this particular research. So that goes without saying. After you have picked a certain topic and you have enumerated your objectives, including the research question and primary objective, you would now want to focus on how you're going to conduct that research. That is the methodology. And since we are dealing with statistics in this tutorial, the first thing you would want to know is, all right, so I am doing so and so study. This is going to be an observational, say cross-sectional or prospective longitudinal study, focusing on two groups. Now, I want to calculate the sample size for both of these groups. Why sample size calculation is important is because suppose you have two groups and you say arbitrarily that I want to have 20 samples in each group. The problem with this is that 20 people in each group might give you false results or might give you no result at all, when in reality there actually is a result to be seen. We will discuss these concepts later on, right? So that is why, in short, sample size calculation is very important. The first study which I will take the help of, this is an example study, of course. Say we want to describe the clinical and laboratory features of patients with diabetic foot ulcers. All right, so this is going to be a descriptive study, a cross-sectional study, and we want to simply describe, it is going to be a descriptive study to describe the clinical and laboratory features of patients with diabetic foot ulcers. So this is a descriptive study, and so how many patients do we need? How many patients do we need in this study? Just a random figure. So this can be calculated with the help of this formula. So here is when you would want to take a screenshot of this formula. Not yet, I will tell you when you can take a screenshot. So this formula looks a little complex, but it is actually very easy. Let me break this down for you. N0 is the total sample size required. The E, which is the divisor, is the precision level. So this is the margin of error which we are prepared to tolerate. Arbitrarily, we would take a margin of error of 5%, so plus or minus 5%, right? So that would mean that the result is within 5 percentage points of the two population values, so plus or minus 5%. That is the precision level E. Z is the confidence level. It is typically set at 95%, right? So 95% is 0.95. So that is the value of Z we will be plugging in. And P is the proportion, so estimated proportion. For example, now this is a study focusing on the clinical features or laboratory features in patients with diabetic foot ulcers. So what is the proportion of patients who also have neuropathy, right? So if that is our primary objective, we want to find out, then we might need to review previous literature where people have talked about the proportion of people who have uncontrolled diabetes or who have diabetes who have neuropathy. For example, in previous literature, if people have reported the estimated proportions of diabetic neuropathy to be 45% or 40%, that is our estimated P. That is our P, right? If people have reported, say, 5% people have diabetic neuropathy, then we will take P as 5%. And converting that into a decimal format, 5% will be 0.05. However, if we do not know the estimated proportion, or if there is no previous literature, we want to take the maximum sample size possible for this descriptive study. In this case, arbitrarily, we can take the proportion to be 50%. So taking the p value as 50% or 0.5 here will provide us with the maximum sample size with this formula. Now, plugging all these values in, E of 0.05 or 5%, Z of 0.95 or 95%, and P of 0.5. Of course, 1 minus P will be 1 minus 0.5 in this case. That is again 0.5. And we will get a sample size of, say, 380 or 384. You might want to plug these values in and do it yourself, but you need not. So this is just for your explanation. So if you want to use a sample size manually calculated like this, you may choose to do so. But using the two websites I have shared with you in the chat box, you need not even manually calculate your sample size. It is very easy. I will show you in just a bit. All right. Now, for example, we will consider a second study. All right. So the first study was a descriptive study focusing on proportions or percentages. So just describing what proportion of clinical features we find in a certain group. Now this study we want to compare, right? This is a comparative study now. All right. Suppose we have the same patients, diabetic foot ulcers, and we want to find out whether, so we have two treatments currently, regular dressings, which is the current standard of care. And now your professor in your college has devised a magic treatment X, right? Along with the regular dressings. So we want to compare whether regular dressings are superior to magic treatment X. So whether there's a difference in between the outcomes between both of these, regular dressings and magic treatment X. So the outcomes will be probably cases who go on to develop infections or osteomyelitis or something like that. So that you will need to define as your primary objective, right? All right. So before we actually go into how we calculate sample size for two groups comparisons, first we would like to know what we mean by power and what we mean by alpha error. You might have heard of both of these values in your community medicine postings or community medicine lectures or somewhere else. And if you do not know this slide, you might want to take a screenshot of this slide. All right. So the columns, both of these, represent what we see in reality. All right. So let me first define what we mean by an alternative hypothesis and what I mean by a null hypothesis. Consider the same example. Two treatments, regular dressings or magic treatment X for the treatment of diabetic foot ulcers. The null hypothesis will be that both of these treatments are equally efficacious in treating diabetic foot ulcers. So null means there is no difference. The name suggests that there is no difference, null. So magic treatment X and regular dressings are equally efficacious in treating diabetic foot ulcers. The alternative hypothesis needs to be carefully stated. You cannot go on to say whether one treatment is better than the other. That would mean a one-tailed hypothesis. You need not concern it. It is not concerning to us right now. But the alternative hypothesis usually is stated that there is a difference between both of these treatments. Now, we are not going to say whether the magic treatment X is better or regular dressing changes are better than one another. We are just saying that there is a statistically significant difference, that there is a difference. That will be our alternative hypothesis. All right. So the two columns, so I have labeled this reality, and this is our study finding. These are our study findings. So in reality, when the alternative hypothesis is true, right? So we denote the alternative hypothesis by H1 and the null hypothesis by H0. So in reality, there is a difference between both of these treatments. And our study rejects the null hypothesis. Remember, H0 is null hypothesis. So the study rejects the null hypothesis. And in reality, the alternative hypothesis is true. That means that what we are finding in the study is actually true. So these are the true positives, right? These are the true positives. In reality, it is true. And our study is confirming that there is indeed a difference. All right, whatever test you may use, say, suppose the Z test for proportions or T test or ANOVA or whatever, right? So the study rejects the null hypothesis or the study accepts the alternative hypothesis. Both are equivalent ways of stating the same. And this is what we mean by true positives. If in reality, both of these treatments were equally efficacious, but in our study, we found that suppose magic treatment X was better than regular dressings. That would mean that we have a false positive, that in reality, it is not actually present. The difference is not actually present, but we have found a statistically significant difference. We have found a significant p-value. Okay. That would mean that we have gotten a false positive. Similarly, if in reality there is a difference, but our study says that the null hypothesis is true, or both of these treatments are equally efficacious, but in reality there is a difference, then as you might guess, we have got a false negative. False negative. Our study falsely assumes that the difference is negative, that the difference is not present, but in reality the difference is actually present. For example, probably magic treatment X is actually better than regular dressing changes. And the bottom right corner is actually true negative. So in reality, there is no difference. And our study also tells us that there is no difference. So this is again, this is what we want. And so true negatives are what we want and true positives are what we want. Okay. Now, alpha error is, so you might have heard of alpha, right? Alpha. So alpha or errors, also known as type 1 errors, is when we get a false positive in our study. Typically, we set an alpha error of 5%, not more, right? Alpha error of 5%. So that means that we accept a 5% chance that our result is a false positive. That is what we mean by alpha error. And a beta error is a false negative. That is, we accept a so and so percent chance that our result is a false negative. So in reality, there is a difference, but our study does not find a difference. So we can be a little more lenient with our beta error, right? Because there is no harm in, so there might not be any harm in getting a false negative, but probably there is more harm in getting false positive. So alpha error we typically set at 5%, and beta error is typically not set more than 20%, right? 20% is the maximum beta error you can tolerate, not more. So when you set a beta error of 20%, that means your power will be 1 minus beta, or 80%, right? 20% and 1 minus beta is 80%, right? So that is what we mean by 80% power of our study. We can set the beta error to be lesser than that. So we can set the beta error to be 10%. That means a power of 90%, or a beta error of 5%. That means a power of 95%. This is actually desirable. That means we increase our chance of finding true positives and lowering our false negatives. But the trade-off is that the sample size increases. So if we can afford to take a larger sample, then great. But if not, 80% power or 20% beta error is the maximum error you can tolerate, right? So alpha 5%, beta 20%. Just remember this arbitrarily. All right. So this is what I've explained. Now, in this comparative study, the primary outcome is delayed healing rates. All right. Previously, we have literature that regular dressing changes reduce event rates to 30%, right? So only 30% people have delayed healing rates from regular dressing changes. But now we expect our magic treatment X to reduce event rates to only 10%. So now 30% was our previous event rates, and now 10% is our event rates with magic treatment X. Now you can take a screenshot of this sample size required in each group. So this is the formula for a two proportions study. So we have two samples, right? Regular dressings and magic treatment X. V denotes the proportion of people who have delayed healing rates with regular dressing changes, and W denotes the proportion of people who have delayed healing rates with magic treatment X. So in this case, it is 30% for V is equal to 30% and W is equal to 10%, right? From the previous side, what we have decided, 30% and 10%. If you plug in these values, right? V is 30 and W is 10. If you plug in these values, you will find that the sample size in each group, remember that this is each group, right? Sample size in group regular dressings and sample size in a group magic treatment X is 60 samples each, or 60 patients each. All right. You can calculate it by hand if you want later onwards. But again, I will show you an easier way to do this with the online softwares. Now let me quickly go over types of data and variables. So first of all, we have quantitative or numerical data. All right. So this data is expressed in terms of numbers. For example, blood pressure readings, right? 120 systolic blood pressure, 120, 144, 152, 96, etc. These are numerical data. And this is also known as continuous data, the blood pressure readings. Again, for example, the same blood pressure readings we get according to the American Heart Association classification. Normal blood pressure readings less than 120 systolic and less than 80 diastolic, but will be AHA 1. Elevated will be systolic between 120 to 129, that is 2. Stage 1 hypertension, or we can label this as 3, will be more than 130 to 139, and stage 4 is more than 140 by 90, and crisis is more than 180 by 120, right? So this is just according to the American Heart Association classification. So we can also label these as 1, 2, 3, 4, and 5. So these are also numbers, right? But these are ordered numbers, right? From ordered. So these are ordered from normal to crisis. 1, 2, 3, 4, 5. So this is what we mean by ordinal data. So there is a difference between continuous data, which are blood pressure readings, and ordinal data, which is ordered data. Going forward, we have qualitative data or categorical data, right? So these are names or labels. So that is why it is also known as nominal data. So nominal is Latin for names, right? So again, names. So for example, you have groups, right? You have say 3 groups of patients. All right, you are doing a study on 3 groups of patients. One is the control group who are not, so you are studying the blood pressure readings, specifically the systolic blood pressure readings in 3 groups of patients. One is the control group, one is the group taking ACE inhibitors, and one is the group taking ARBs. So angiotensin converting enzyme ACE and ARB is angiotensin receptor blockers, right? So these are the 3 groups, and you're comparing systolic blood pressure readings. So this variable, control, ACE inhibitors, and ARBs, is what we call as categorical data or nominal data. Here, the blood pressure readings in this study will be quantitative or numerical, and the groups will be the qualitative variable or the categorical variable or the nominal variable, right? So what are dependent and independent variables? You might have heard of these terms, dependent and independent. So dependent variables are response variables which are measured or tested in a study, right? For example, you are conducting a study, all right? For example, you are conducting a study to assess the efficacy between say an interscapular block or an infraomohyoid block. So typically, this is the domain of anesthesiologists, right? Regional blocks. So infraomohyoid block versus say infraclavicular or say perihumeral plexus block, right? Infrahumeral and perihumeral plexus. You want to find out difference in patients who are undergoing hand surgery. Okay, so of course the brachial plexus, the median nerve, ulnar nerve, radial nerve provide sensation to the hand, and by giving these blocks, a perihumeral or an infraomohyoid block, you are essentially reducing the pain levels in patients undergoing these surgeries. You want to find out the numerical rating pain scale scores, right? So you might know that the NRS score from 1 to 10. So 1 being the least amount of pain to 10 being the worst pain imaginable. So you want to find out the numerical rating pain scores. So in this study, these NRS scores, the numerical rating pain scale scores, will be the dependent variable, and the independent variable will be the variable which affects the dependent variable. In this case, the block, right? The infraomohyoid block or the perihumeral block. So both of these blocks will influence the pain scores. So these are the independent variables which affect the dependent variable, right? The variable which is tested in a study is the dependent variable, and the variables which influence the dependent variable are the independent variables. This will get clear in the next sessions where we will be practically demonstrating statistical analyses. So I have already explained this, right? Now, you have data ready. You have calculated sample size. You have performed the study. You have your data in a nice Excel sheet. You have clean data. And now you want to apply a statistical test to compare between 2 groups. So 2 or more groups. Okay. So which statistical test do we want to use? Do we want to use a chi-square test, Fisher's test? So you might have heard of all these tests. So the next slide. So this slide will explain all the tests with all the data. But before running any type of statistical test, we always want to perform what we call as an exploratory analysis or a descriptive analysis. So an exploratory analysis is an analysis which explores your data in such a way that you can either visualize the data you have, or you can get certain summary statistics by which you can have a feel of how your data looks like, right? Whether your data is skewed or not. So all of these terms will be discussed in the next session, but whether your data is skewed or not, whether your data is normal or not, and so on and so forth. So what is the mean of one variable? What is the proportion of one variable? What is the standard deviation? Measure the central tendency, measure dispersion. So all of these come into the category of exploratory data analysis. So exploratory data analysis includes descriptive statistics, that is proportions, means, standard deviations, getting cross tabs or continuance tables, right? So 2x2 tables you might have heard of. All of this will be explained in the next lecture session, so don't worry about if you don't understand all of these, but this is just a lecture to prime you for the next sessions. We can visualize data with the help of histograms, box plots, bar plots, and pie charts. Now, this slide you might want to take a screenshot of, right? This slide explains all the statistical tests required for each type of data. That is why I took the effort of explaining what we mean by dependent variables, what we mean by independent variables, what we mean by numerical data, and what we mean by categorical data. So, for example, now consider that our dependent variable is quantitative. All right. So, for example, consider the example of patients who were given ACE inhibitors versus ARBs versus the control group. So 3 groups, and we are measuring the systolic blood pressures. Systolic blood pressures are our variable of interest. That will be our dependent variable. And it is, of course, a numerical data, blood pressure readings. So we have this column. And our independent variable is the groups, ACE inhibitors, ARBs, and control group. So that is, of course, not numerical, that is categorical or qualitative data. And we have 3 groups. So we would like to use the analysis of variance, so ANOVA. The t-test is to compare between 2 groups. So for example, if we only had ACE inhibitors versus ARBs, we would use the t-test, independent samples t-test. If we had ACE inhibitors, ARBs, and a control group, then ANOVA. Or even more than 3 groups, we would use the ANOVA, or analysis of variance. And we can also use linear regression to get the mean difference between the systolic blood pressure readings. While this technique, so you might ask, what is the advantage of regression to t-test? Regression is more robust, it is more powerful, and you can adjust for certain confounding variables using regression techniques. For example, you can adjust for age, you can adjust for gender, you can adjust for any other demographic variable. So that is why regression is an excellent technique to use. Now, suppose both of your variables were numerical, then you can use correlation technique, right? You can use Pearson's, Spearman's, or Kendall's. So Spearman and Kendall are non-parametric and Pearson's is a parametric. So all of these will be explained in the practical sessions. So you can use Pearson correlation, or you can use linear regression to predict one variable using the other variable. Suppose the variable of interest is categorical. Suppose your variable of interest is, say, whether a person died or not. So say in COVID, the outcome, death or not, is your variable of interest, and the independent variable is, say, whether the patient was admitted to the ICU or not. So both of these variables are categorical, right? So ICU admission, yes or no, and death, yes or no. All right. So in this case, both of these variables, the dependent and the independent, are categorical or qualitative. They are not numerical. We can use the chi-square test, right? If the numbers are very small, less than 5, we can use the Fisher's exact test, or we can use logistic regression to predict death or not. So logistic regression is a technique used to predict whether an outcome has occurred or not, or a dichotomous outcome. Dichotomous means 2, yes or no, more or less. So dichotomous, so 2. So 2 outcomes. So logistic regression is used to predict dichotomous outcomes. And so basically, I think you must have taken a screenshot of this slide. This slide is excellent if you want to refer, if you want to understand which test to use for what type of variable. Moving forward, I've already explained what null and alternative hypotheses are, so I won't go into detail. But the null hypothesis is essentially, yeah, Pratik has raised his hand. So do you want to ask something? I think he raised his hand by mistake. All right. So let's move forward. So the null hypothesis is a statement of no difference between certain characteristics of a population. And the alternative hypothesis is a statement that rejects the null hypothesis, right? So we've already discussed both of these, so I won't go into too much details. But as I've already told you, the alternative hypothesis needs to be carefully formulated. So the null hypothesis, you can formulate that there is no difference, right? But the alternative hypothesis can be two-tailed or one-tailed. So two-tailed means that there is a difference and we do not want to comment where the difference lies. Whereas in a one-tailed alternative hypothesis, we are commenting that, yes, there is a difference and the direction is this. So for example, the two-tailed alternative hypothesis would be there is no difference between regular dressings and magic treatment X, whereas the one-tailed alternative hypothesis will be that the magic treatment X is better than the regular dressings, or the regular dressings are worse than magic treatment. So that is how we can formulate the one-tailed alternative hypothesis. Now, an important concept of statistical significance and a p-value. So typically, we plan the study, right? We formulate the null and alternative hypothesis before performing the statistical test. Now, it won't be the case that we always get 100% true positives or 100% get true negatives. We always, so this is reality, right? This is not some kind of utopian world we are living in, right? So we won't get 100% true positives or true negative. We want to settle for some level of confidence, which we call as the significance level, for which we want to be correct. All right. The alpha error, which I've already talked about, is the probability that we are willing to be incorrect, right? Or the false positives. Alpha error is a probability that we are willing to be incorrect, also known as the false positives. Arbitrarily, we want to be correct about that can also be stated that we are willing to be incorrect 5% of the times. That is alpha is set at 5% or 0.05. I think my internet connection is unstable. Can you hear me properly?
Yeah, now we can.
Yeah, great. Okay. So that is the alpha error, 5% or 0.05. Now, once we set the alpha error, so this alpha error is set before the study. We set the alpha error, we perform the study, we analyze our data, and we all now get a p-value. For example, we run a t-test or we run a chi-square test, we get a p-value. In some textbooks, in some articles, you may find the p-values also denoted as PR, right? So the p-value is nothing but the probability value, PR. And typically, p-value is the same as the alpha error. So the alpha error is 5% or 0.05. So p-value should be less than or equal to 0.05. If our p-value is less than or equal to 0.05, we reject the null hypothesis. And that is, we reject that the two treatments are equally efficacious. And we say that, yes, one treatment is more efficacious, or there's a difference between the two treatments. And if the p-value is more than 0.05, of course, we have to accept that both treatments are equally efficacious. Okay. The p-value is a probability. P is also known as probability, right? P is a short form of probability. The probability of obtaining test results at least as extreme as those observed during the test. So if you don't understand what this means, it is fine. Just remember that the p-value is a probability of obtaining a false positive in simple errors. Or p-value is the probability that our results occur due to chance. When the p-value is 0.05 or 5%, that will mean that we have a probability of 5% that our results are due to chance alone, false positives. That is, in simple terms, what the p-value denotes. So if PR, or the probability, I've just changed the denotion for p-value here to get you more comfortable to PR. So if the probability is less than alpha, then assuming that the null hypothesis is true, the probability of obtaining the test results would be less than the probability of making a type 1 error. You can take a screenshot of this slide and you can ponder this later on. This is as simple as I can get to explain the p-value without losing its true meaning. So the 5% of results occur due to chance is a very diluted explanation of the p-value, but this is the correct definition, and I would encourage all of you to ponder upon this afterwards. All right. Now, there's a difference between statistical significance and clinical significance. So suppose you perform a study between patients taking ARBs and patients taking ACE inhibitors, and you are studying the systolic blood pressures. Now, you take sample size of 1,000 and 1,000 patients in both of these groups. All right. So you have a very large sample size. 1,000 patients is no joke. 1,000 and 1,000 in both of these groups. And suppose in the group taking ARBs, you get a mean systolic blood pressure of say 132. And in the ACE inhibitors, you get a mean systolic blood pressure of say 128. The combined standard deviation for both of these is suppose 2. All right. So 2 millimeters of mercury. The ARBs, the SBB is 132, and ACE inhibitors, it is 128. So clinically, is there a difference between both of these? No, right? 128 and 132 clinically does not mean that there is a difference between both of these groups, because if a patient has 132 SBP and if a patient has 128 SBP, it is a normal intraday variation as well. So it does not denote clinical significance. However, a t-test might give you a significant p-value. It might tell you that the p-value is statistically significant, less than 0.05. And it may tell you that, yes, there is a difference between the group taking ARBs and ACE inhibitors. And it may tell you that, say, ARBs have, ACE inhibitors have significantly lower systolic blood pressure. So, right, so we get a statistical significant result, but clinically it is not significant. So in essence, that is a difference between statistical significance and clinical significance. And it is important to know, if you get a statistically significant result, is that clinically significant? Is that clinically relevant? So you always have to take into consideration whether a statistically significant result is also clinically significant. So these are the distinguishing points between statistical significance and clinical significance. I won't explain these. I've already explained the difference. So I will move on. This is the last leg of our lecture. After that, we will be discussing how to calculate sample size interactively. But this is the last slides of our lecture. So confidence intervals and standard errors. All right. So suppose you are performing a study in India. All right. Where consider the same study, ARBs versus ACE inhibitors, systolic blood pressure readings. You are performing this in a city in India. All right. So if you perform this in, say, Delhi, all right, you are sampling a very small population out of the entire population of India. So the big X denotes the entire population of India. All right. And the X1 denotes population in Delhi. So you are sampling, right? You are sampling patients or volunteers from a city in India, not in the entire country. So you are sampling a population, and X is the average systolic blood pressure or the mean systolic blood pressure, right? You perform the same study again. All right. So suppose uh, you get a mean systolic blood pressure of 130 in Delhi. With the exact same methodology, you perform the same study in Kolkata, which is your X2 sample, right? This is the X2 sample. So Delhi and Kolkata are both in India, so they are representatives of the entire population X. X2 is the average systolic blood pressure in patients being given ACE inhibitors in Kolkata, and say it is 129. All right. To perform the exact same study using the same methodology, same criteria, same everything in Mumbai. All right, in Bombay, and you get a systolic blood pressure reading of 131, an average systolic blood pressure reading of 131. All right, and you perform multiple such studies in other cities, Pune, Chennai, Bangalore, etc. Right, n number of studies. All right, you will get n number of average systolic blood pressure readings. They might not all be the same: 130, 131, 129, 132, etc. Right, and all of these cities are samples of the representative population from India. So essentially, confidence intervals denote the range of values that you can be X% confident contains a true parameter of interest of the population. Right, the entire population in this example will be India, right? Population will be India, and the range will be, say, an average of 128 in Chennai to an average of 132 in Kolkata, right? So the range will be 128 to 132. All right. So confidence intervals are the range of values that you can be X% confident, which contain the true parameter of interest of the population. And what is this X? It is typically 95%, right? 95%, or 1 minus the alpha error rate, or 1 minus 5%. It is typically 95%. You may find in some places 99%, 99.9%, and so on and so forth, but typically it is 95%. Now, suppose you are doing the same study, right? You want to find out whether the systolic blood pressure readings in ACE inhibitors or ARBs are different. SBPs are different. When you perform a t-test in any software, I will show in JAS, you will also get a mean difference, right? So say an average systolic blood pressure of 132 in ACE inhibitors and 130 in ARBs. So the mean difference would be 132 minus 130, or 2, right? The 95% confidence interval for this mean difference should exclude 0. That is when we reject the null hypothesis, and this is when we will typically get a p-value of less than 0.05. All right. So you may want to click a screenshot of this slide. So when the 95% confidence interval for a mean difference excludes 0, we reject the null hypothesis. But if we obtain a ratio, an odds ratio, suppose, or a relative risk ratio, RR, that will mean it is a ratio, right? A numerator and a denominator. So the 95% CI for these ratios should exclude 1. That is when we get a significant result, or a null hypothesis is rejected. So this will be practically demonstrated in the upcoming sessions. And typically, the CIs between the two groups should not overlap. That is one more criteria. Now, the standard deviation is a measure of dispersion, which quantifies how much the raw data point are spread out. So, for example, in the study in Delhi, we get an average systolic blood pressure of 130 plus or minus a standard deviation of 2. So that is the raw data point dispersion, is a standard deviation. But a standard error is how much the means are spread out. All right. So how much the means are different between Delhi, Kolkata, Pune, Chennai, Bangalore, Mumbai. So this is the difference between standard error and standard deviation. All right. I hope all of this is clear. To recap, we saw the sample size calculations for descriptive studies and for comparative studies. We will also see that now with the help of the two websites. We saw the types of errors, or the alpha error and the beta error. We saw types of data, so quantitative versus qualitative data. We saw what we mean by dependent and independent variables. We saw what exploratory analysis is and why it is important before performing any hypothesis testing. We saw what appropriate statistical tests can be used for what type of data. We saw what we mean by null hypothesis and what we mean by alternative hypothesis. We saw what we mean by two-tailed and one-tailed. P-values or probabilities, we saw what they actually mean and how we arrived at 5%. We saw what confidence intervals are, and now in the next sessions we will discuss about assumptions. So assumptions for statistical tests are important before performing any test. So we will discuss assumptions and what we mean by parametric and non-parametric tests. So both of these are discussions we will keep for later on. All right. Again, a list of resources. If you failed to take a screenshot, if you want to take a screenshot of this as well, you can do so of the recap. Yeah, Pratik.
Yeah, I had a few doubts if you're free.
Yeah.
One of them was that in the logistical regression part, you told that these are used to predict the dichotomous data. So, how do we basically, what do you mean by predicting the dichotomous outcomes as compared to chi-square and Fisher's exact?
So chi-square will not, so chi-square, you will not have, say, odds ratios. In Fisher's test, you can have odds ratios, but logistic regression will help you to predict the probability of a dichotomous outcome occurring. Chi-square test will not give you those values or your statistical values. So chi-square, so your odds ratios, you will not get your sensitivity, specificity for your logistic regression and stuff like that. So in logistic regression, you have your parameters which help you to predict your outcome. And this will get clear when we talk about logistic regression practically when we are doing it in JAS.
Okay. So if with an example you would like to explain, if you like you said the death and no death was in ICU versus a general admission.
Yeah.
So if you have like a sample size of 100 people or so, then which test would we use ideally?
So sample size of 100, you may want to choose 100 is a medium sample size. It's not too small, too large. So you may want to go with logistic regression.
Okay.
Now, in logistic regression, so you will typically not do regression analyses with only one independent variable. You would want to adjust for certain 2 or 3 more variables. All right. So this is again one more advantage of regression techniques, because you can use more than one independent variables. In chi-square, you cannot do that, or in Fisher's test, you cannot do that. You can do what is known as a Cochrane-Mantel-Haenszel test, which is stratified contingency tables, but again, that is an advanced technique. Regression techniques are are better because you can adjust for those. So 100 sample size logistic regression is a good technique. However, you can always calculate power for these techniques, right? So you can calculate power using that sample size, using how many explanatory variables you are using, say 2 or 3 independent variables, and you need to provide some other statistics, and you can calculate your power. But 100 sample size is quite a large sample size, pretty high sample size for logistic regression.
Okay.
For one independent variable.
Okay. Thank you so much. There's one more. For all of these, the tests that you suggested, are all of these used only for normally distributed data or also for any
Yeah,
of
that's a good question. So all of these are parametric tests. So those are typically used for normally distributed data. Regression is an exception. It can be used for normally distributed data as well in some cases. But the other tests, t-test, ANOVA, they are used for normally distributed data. So that is what I want to talk about in the next session's assumptions for statistical test. So you assume normal distribution, you assume homogeneity of variances, you assume homoscedasticity, so on and so forth. So, right.
Okay. Thank you so much.
Yeah. All right. So again, the resources, and now we may want to, all of you might want to go to the chat. You may want to go to the chat and go to OpenEpi, the first link. So I hope all of you have opened the OpenEpi website. And here in the left side, you can see all of these options. We are concerned with only the sample size calculation and the power calculation. So if you go to sample size, you click the drop down menu for sample size and you click proportion, right? Just click on proportion. So this is the sample size calculator to calculate for a descriptive study. So the first formula that I told you about, it uses the same formula. So you do not have to manually calculate the sample size, right? You select the enter new data here. Enter new data. Okay. And now the population, you would like to fill all of these parameters which in the blue box. The population size is the population size to which you are catering to or from which you want to sample your data. All right. For example, if you are working or if you are a student in a hospital in Mumbai, say you are an intern at KEM Hospital Mumbai, okay, the duration of your study is from say June 2023 to December 2023 in the outpatient department of general surgery. Okay, so diabetic foot ulcers, usually we'll see them in the OPD of general surgery. The population size will be calculated. How many number of people come to the general surgery OPD in 6 months, right? From June to December, so 7 months. All right. So I am guessing it will be quite a large number in the range of say 10,000 or more. So this will be the population size. All right. If it is very large, it suggests that you leave it as 1 million, right? Now, again, the anticipated frequency of, say, neuropathy is perhaps, say, it is 15%. All right. That is the anticipated frequency. So you might have estimated this, or you might have done a review of literature, and you might have found out that in a systematic review or a meta-analysis, the anticipated frequency is 15%. All right. And confidence limits. So 15% plus or minus, say, let's say 3%. Okay. So 15% plus or minus 3%. And leave the effect, design effect, or this design effect of 1 for a random sample. So you will perform random sample. Just keep it as that and select the calculate. Click on the calculate option. So now it will provide the equation. So this is a little different equation than the one I told you about. Right. So this equation you can just copy and paste into your methodology, samples as calculation, in your manuscript. And these are the parameters which you have entered. So 10,000, 15% plus or minus 3, and a 3% confidence limit, 15 plus or minus 3. And these are the sample sizes. So at 80% confidence level, it is 228. At 90%, it is 370. At 95%, it is 517. Right? So depending upon your confidence level, you may want to choose a sample size. All right. So this is how you calculate using OpenEpi, the sample size for population. Now, OpenEpi also gives you options to calculate sample size for unmatched case control, cohort studies, or randomized control trials, and mean difference. But we will be using WebPower for the rest. WebPower also helps with the same calculation for the proportion, but I wanted you all to get used to OpenEpi, the software. All right. So go to the second link, the WebPower link. And go to new power analysis. So all of you have opened the WebPower website and have gone to new power analysis. Now, suppose consider second study, right? The second study in diabetic foot ulcer patients, where we are exploring regular dressings versus magic treatment X. So here, these are two samples, right? So one sample with regular dressings and one sample with magic treatment X. So we want to calculate the sample size for both of these groups. So we can do that. So if the regular dressing changes and magic treatment X, if we want to have equal sample sizes, we can choose the second option. If for some reason, ethical reason or something, we want to reduce the number of patients in the magic treatment, the new treatment, we can use an unequal sample size option. But for the purposes of explanation, I will go to 2 sample proportion equal sample size. Select this link. All right. So do not just remove the sample size parameter and go to power and type in 0.8 or 80% power. So again, remove the sample size which was entered here by the software itself and add 80% power or 0.8% power. Now, effect size, you select the show button, and the effect size calculation, you need not type in anything yourself here. So now what we agreed on, so the proportion 1, that is the regular dressing changes, the delayed healing rates, right, was 10% in regular, was 30% in the regular dressings, right? So 0.3, 30%. So 30 by 100 is 0.3. And in Magic Treatment X, the event rate of delayed healing was only 10%. So proportion 2 is 10% or 0.1. All right. Now we click on calculate here. It automatically calculates the effect size which it uses. If you want any further help with the calculation, you can just select the help button and it will redirect you to the help, the description for this calculation, and you can see the effect size which it uses. Right. So now that we have entered all the parameters, the effect size, significance level is the alpha, right? Significance level is the alpha. We keep it at 0.05 or 5%. Power is 1 minus beta error. Beta error is typically 20%. So power is 80% or 0.8. The alternative hypothesis H1, we keep it two-sided, right? Power curve, I will not go into that, right? So no power curve. And select calculate. So if you see here, N is 58 or 59. It was similar, right? It was similar to what we had calculated by hand using that formula for two proportions. So 59 or approximately 60. And for each group, this is for each group. So 59 or 60 per group. And these are the parameters which have been used: alpha, power, and the effect size H. Okay, so we discussed about calculating sample size for one sample proportion, two sample proportion in this example. And now, finally, we will calculate the sample size required for running a t-test. So go to new analysis, new power analysis. Okay, go to power of t-test. Go to power of t-test. Deselect or remove the sample size which has been provided here. Input a power of 0.8 or 80%. Keep the significance level or alpha as 5% or 0.05. And effect size is Cohen's d right here. So go to calculator. Right, it will redirect you to a separate page. And in this case, we are performing a two sample t-test, right? Consider the example of ACE inhibitors versus ARBs. ACE inhibitors versus ARBs, we are measuring the systolic blood pressure. All right. So these are two separate samples. So we will be running a two sample t-test. Suppose the mean systolic blood pressure in the group taking ACE inhibitors is, say, 132. And the mean systolic blood pressure in the group taking ACE what is the first? I think ACE inhibitor. So the second group will be ARBs. So group taking ARBs is say 120, 124. And the common standard deviation, right? Suppose the standard deviation in both the groups, it is also known as pooled standard deviation, is suppose say 4 or 4. Now we select calculate, and we get Cohen's d of 2. This is 2.00. It is 2. So we go back to our previous page and we put 2 here. So effect size, because we were outputted with 2, right, using the parameters. And now we press on calculate. Now it's very absurd because the means in both of these groups was 132 and 124, and the standard deviation was also quite small. So 4 is a pretty small standard deviation considering this. So that is why we have been given a sample size of 5 in each group. But to demonstrate the effect of power on sample size, just enter a power of 95% or 0.95 and see the difference. So it is not much difference, right? Because the mean difference were quite large themselves. But suppose, say, a 99.99% power. You see how the sample size is going up? It is now 17 per group. To illustrate the effect of mean difference better, suppose the mean difference was just 132 and 128. All right, like we had discussed. So clinically, 132 and 128 is actually not much of a difference. It is just a difference of 4 systolic blood pressure points. All right, so now we will calculate the effect size for this. It is now giving us an effect size of 1. Right, 1 is quite nice round number. So just to make it a little more interesting, let me put a mean of 130 and a common SD of 3. All right, so now the effect size is 0.6667. Right, with a 95% power. Let's calculate the sample size. So now we have a sample size of 60 in each group. So the reason why I played with the means, the standard deviation, and the power is to give you an idea how rapidly the sample size can change. So it went from a sample size of just 5 in each group to now 60 in each group. It is such a huge difference. And that is why you must always be careful while putting in your means and common standard deviation. That is why it is always advisable to perform a pilot study of say 10 or 10 patients each in each group, and then calculate the means for both these groups, calculate the common standard deviation, and then input those values. Then you calculate your total sample size. That is why it is a good idea to perform a pilot study. Okay, I think it is more than 1 hour. It's 1 hour 15 minutes, and the agreed upon time was 45 minutes to 1 hour. So I think the last part was, I think, a little more interesting for you guys because you got to do it yourselves. So I think we'll stop the session here for today. Does anybody have any doubt? Yeah, Pratik.
Hi. So one of my doubts was, as you said, you usually need to perform a pilot study before starting with the entire thing. So if someone wishes not to start one, do they use a previously calculated data through previous researches, or what do they do?
Yes, exactly. So you do a review of literature, you get the estimated means, right? So always while doing a review of literature, meta-analyses are the best type of literature because they are pooled, right? So you get a pooled mean and a pooled standard deviation of all of the studies which the meta-analysis has taken into account, and you can use that to calculate your sample size. But if your study is not, it is very novel and there does not exist previous literature supporting your supporting those means, what you can do is that you can estimate, right? You can estimate what the mean will be. You can write down what the mean you are expecting based on a clinical experience.
Okay.
You can estimate the variance or the standard deviation or dispersion of data. You can estimate that, and you can plug those values in. But typically, for very novel studies, you typically do a pilot study and then calculate that. But yes, the short answer to your question is yes. You do a review of literature and then you pull in your means and standard deviations from that.
Okay. So like, unless we have a basic estimate of what the values will be, there's no way to calculate the sample size, right?
Yes, yes. One more way is that, so this requires you to have a deeper understanding of effect sizes. So for t-test, it is Cohen's d, right? So you need to know what Cohen's d, the values of Cohen's d are. So what small effect size, medium effect size, large effect sizes are.
Okay.
So if you expect that you will get a medium effect size of Cohen's d of say 0.3 to 0.5, so then you can plug in the value directly 0.3 and you can calculate accordingly your sample size accordingly, or 0.5, then you calculate accordingly and you get your sample size. But you need to have a deeper understanding, and journals usually do not entertain arbitrarily calculated sample size very easily. So a pilot study is the best, then a review of literature with carefully cited references second best, and if you do not have any other option, then just the effect size.
Okay. So one more, the common standard deviation that you calculated, that is basically the average of the standard deviation of both of these, right? Or something else?
Yes, so it is the pooled standard deviation. So from all the data, the entire data, you calculate the standard deviation for both of these groups pooled.
Okay. Thank you.
Yeah.
So effect size is in fact the correlation variable, right? Like the
Yes, in
strength of relationship between two variables.
yes, that is the strength of relation between two variables. Exactly. So for correlation, for Pearson's correlation, we have R. For Spearman's, we have rho. For t-test,
Eta.
yes, eta is for eta squared are for ANOVAs. For regression, we have R squared. For logistic regression, we have odds ratios, relative risk. So all of these are effect sizes.
Yes. Okay, so thanks a lot, Sudeep, for being here and helping my members gain this basic understanding.
Yeah, I think Kumar Saurabh has a doubt probably.
Kumar, Saurabh, you have some doubt? Please let
Yes,
us know
yes.
in the chat.
I was waiting for my chance, and thank you, Dr. Pratik. You are my senior. I'm actually in the final year, and I'm a student at Georgia, but basically, I'm Indian in origin. So it was very nice finding a person from similar background in data science. I got most of the things as expected, but I had two questions. The first is, you told that by p-value we can predict the statistical significance, but it doesn't usually correlates, it is not necessarily correlated with the clinical significance. So is there any means standard amount? For example, when we define the various stages of the blood pressures, then at every 10 at intervals of 10, we just add one stage. So is there any standard way that we can define that our data is clinically significant with this much difference or this much percentage? If we got a difference in two types of data, then we can tell that it is also clinically significant. As we tell that, for example, if p-value is less than 5%, then it is statistically significant. I think you got my question, right?
I think so. So basically, clinical significance is more of a subjective finding. Statistical significance, you get a hard p-value and you get your test statistics, your test results. But clinical significance is usually used by subjective expert judgment, right? So suppose you get a systolic blood pressure 140 in ACE inhibitors and 125 in ARBs. Okay, 15, an average of difference of 15 is quite large, but an average of 4, 138 and 120, 132 and 128 might not be that clinically significant. But in both cases, you might get a p-value of less than 0.05. So here is when you're writing your discussion of a manuscript, you will explain that even though we got a significant p-value, the difference of 4 systolic blood pressure points may not be ideal for patients, considering perhaps ARBs are more expensive, perhaps. All right. So here is when you want to consider various factors such as the cost, availability, socioeconomic data, and stuff like that, which are relevant, right? So here is when your subjective expertise, your subjective judgment will come into play.
Yeah, thank you. And my next question is that we got a very compact gist of the information which you might have gathered in a comparatively much longer time. So if we if I personally wanted to do it once again, the analysis which you showed us right now, and if I got some extra doubt which I might not recall right now, then can we have any social media handle or email IDs from your side so that we can get some ideas if we need anything from your side? It will be very helpful for us.
All right. So I will type in my personal email in the chat box. And you can, shoot me an email. Here, I also have my own YouTube channel.
Thanks a lot.
So, of course, you can, contact Requir Statistical Solutions directly. You can also contact me by email. You can go to my YouTube channel. The link is in the chat box. And here I have explained all of these concepts in short videos, less than 5 minutes, so that you can recap all of this information.
Thanks a lot for the flavor. This was very nice flavor. Thanks.
Yeah.
So, any more questions, guys? And of course, we have planned 5 sessions for this workshop. So you need not worry about that. You can always practice this information. And if you have any doubts, you can ask in the next session or so. And of course, Sudeep and Yash has their own website, Require Stats, the link of which I have attached to the PDF as well. And they provide comprehensive statistical analysis for your studies also, and for other people also, like the PGs and postgraduate theses and everything. So you can recommend them as well.
Yes, for sure.
yeah. So thank you again, all of you join this session. And I hope that it was useful to you and that you learned something new. I hope you practice a lot as well, so that you can become very, very familiar with the concept. So
Yes.
see you tomorrow. We have the next session tomorrow, right? 19th.
Yes, tomorrow. Yes.
Yes. So see you at 5 p.m. tomorrow. And thank you, Sudeep, for joining.
Yeah,
And
thank you everyone. Thank you for your questions. And I hope you keep on asking nice questions like these, because then I know that you're, understanding the concepts.
yes.
And for tomorrow's session, please do not forget to download JAS. So the link has been put. Just a second. I think the document which has been shared has the link. I will.
Yes, it has the link, and I will share it also again on the group.
Yeah, so I'm sharing the links in the chat as well. I don't think so.
Yes.
So the link contains the download, the website for the download, and the YouTube, my own YouTube videos on how to download and install JAS. So you can refer to those. All right, then. I think thank you everyone for joining. And thank you, Nafisa, for the session.
Yes. Okay. Bye, everyone. We'll see you tomorrow.
Yeah, see you tomorrow, guys.
Bye-bye.